Today I'd like to talk about why I use Julia in my research, which is almost entirely scientific computing. Thanks, Eric, for the great introduction, and congrats to everybody who won a book in the raffle. I'm really excited to be here at PyData. I know this is a conference that's focused, obviously from the name, a lot on Python, but I hope to give sort of a flavor of what Julia is about, and kind of suggest it as something to try out in an inclusive way. And yeah, just to quickly summarize, I work at the Flatiron Institute. We are hiring. If anybody here is a computational scientist or an open source developer and interested, check us out. But yeah. So very quickly, if you want a 1-minute answer for why I do physics using Julia, and then you want to go and like get another burrito or something, the short version of the story is that often in computational science research, we have this so-called two-language problem, where you want to have one code base that's like extremely performant. You've got like a bajillion MPI calls. It's running on 100,000 nodes. You've got the tight inner loops. It's like super optimized. Might have been written in like Fortran 77 by your advisor's advisor. You probably don't want to try modifying that yourself. And then you say, okay, so this beautiful performant code dumps some blob onto me, and I need to analyze that blob and make a plot that I will put in my paper. And usually, in the past, in scientific research, you've had to use 2 different languages to do both those things. And in some sense, that's great because you're using the correct tool for the problem. Like you wouldn't try and drive in a nail with the back of a screwdriver necessarily. You would use a hammer to do that, which is fine. But it's also, there are costs associated with it, because now if you're trying to teach students or you're trying to share your research with collaborators, you're sitting there saying, okay, well now instead of just one programming language, you have to learn 2. And you have to learn best practices for both, and you have to keep both code bases in lockstep in case you change the output format without telling anybody, or your advisor does that maybe, or one of your collaborators, and then all your plotting code doesn't work, nobody knows why, and you maybe don't understand the original language the code was written in. So that's not great. And Julia kind of allows us to get around this problem because it's very easy to write code that's both very performant, easily parallelizable, and very readable for humans in general, both people who are computational science experts and people who aren't. And most scientists aren't very experienced with coding, so it's great if they can read, the code you wrote. And again, I just want to start off this talk on the foundation of saying that this claim about Julia is not a claim that other languages can't be both fast and readable. It's merely a claim that Julia is, and I like using it. And specifically, it works well for some of the problems I want to solve, which I'll go into in a little bit. The other thing, of course, is that I actually have a deep romantic attachment to one-based indexing. Unlike many languages, Julia is one-based, and it's great. I'm never going to get sick of it. It's just so wonderful. This is a very common complaint, and again, it takes all kinds, but one-based indexing is great. So there you go. And another thing that's really great about the Julia community is that there's a lot of people, like the Python community, from very different sort of walks of life, people with all sorts of different experience, but many people are very eager to share what they know and learn what other people know. And there's really sort of a great cross-pollination of techniques and areas of expertise that's a really great way to both like learn new things and improve the research that we're doing. Okay. So like I said in the title, I do quantum physics. So quick question, who here knows what condensed matter physics is? Put your hand up. Not many people. So I should probably explain what this is before I just roll in being like, hey guys, many-body quantum magnets, let's go. So condensed matter physics is kind of a, I don't want to say obscure, because it's actually the biggest subfield of physics, but it's maybe something that doesn't have as much public relations impact. So a 1-sentence summary would be that condensed matter is the so-called sociology of quantum objects. You have a bunch of small objects that obey quantum mechanics that we think we understand pretty well. For instance, like a bunch of electrons or some ions that live in a crystal. And what's interesting about them is that in their interactions with each other, they can give rise to new behavior that's fundamentally different from the small-scale behavior, only like 5, 10, or 8 of them. So these 2 pictures here are actually pictures of 2 related phenomena. So on the right, we have something called Bose-Einstein condensation, where you have a huge amount of very cold bosons, which, if you cool them down enough, they Macroscopically, i.e. almost all the particles in the system enter the lowest energy state, which has a bunch of interesting quantum mechanical properties that you can't observe normally in a classical system, which is kind of surprising. And actually, on your left, we've got a superconductor, which again is like a fundamentally quantum object. So the reason this object is levitating is because when its constituent particles enter the lowest energy state, like occurs in that graph on the right, they can actually experience what's called flux expulsion, where you have a magnetic field that's now forced out of the material, and the superconductor is able to, quote, levitate. This is also called the Meissner effect, if anybody's ever heard that. So the upshot is that many quantum objects interacting with each other can give rise to fundamentally new behavior. And because it's new, it's often difficult for us to understand. And so we need some techniques to approach this. And because it's quantum mechanical, it's often unintuitive. So why use a computer to understand this? In some sense, you don't necessarily need to use a computer. People made a huge amount of progress just with pen and paper techniques for trying to understand the behavior of millions of electrons, for instance, interacting with each other in a crystal. But maybe if you're like me, you're not the best at sitting there, cranking out integrals all day. So you want to do something else. And we know that quantum states form vectors in a Hilbert space. So they have some inner product. For our purposes, it's a finite-sized Hilbert space, which is nice because the vectors are finite length. And usually, because we're interested in only a small portion of that Hilbert space, for instance, the low-lying states and their excitations, because that's where we can observe quantum mechanical phenomena, we only really are interested in a very small amount of the vectors. Though, of course, it's usually not particularly obvious which portion are going to give us the interesting physics. So we have a huge Hilbert space and a very tedious search problem, and a series of steps we can use to figure out if a vector is interesting or not, which is kind of the perfect situation to use a computer. Because then, as I'm sure many of you know, in other data science applications, you kind of just tell the computer what to do and then get coffee for the next 50 hours, and then come back and find out your answer is wrong. So very often in the quantum mechanical context, we spend a lot of our time searching for a very, very small needle in a very, very large haystack, just with a set of rules that's maybe a little unintuitive to people more used to dealing with regular data that's like about human beings or objects which are not quantum mechanical. So as quantum physicists, what would we want from a programming language? There's a couple things. And one of the big ones is human efficient parallelism, by which I mean parallel kernels that are easy for human beings to read and write and reason about. There's parallelism that's very efficient for the computer to run, but it's very difficult for a human being to understand what's going on. For instance, if anybody's ever had to call MPI all V, you might know this pain. So there's a lot of different ways to set up a massively parallel computation across thousands of CPUs, but we'd like something that's easy for us to reason about. It's easy to write because, again, most of the people doing quantum mechanics on a computer went into physics. They didn't become CS majors. And so it's easier for them if we can have a language with parallelism that's easy to write. We'd also like linear algebra as a first-class citizen because that's kind of the basic language of quantum mechanics. Like I keep mentioning, we want something that's easy to write and teach to students and to our collaborators. And the upshot is that Julia can do this. Of course, there are many other situations where you might want to use something else, but a lot of us are using Julia, and I'll try and explain why. Okay. Specifically, what do I like about Julia day to day when I'm doing research? So Julia was designed to do scientific computing from day one. Although you can do things like write asynchronous web APIs in it, it was really designed from the get-go for people like me who want to do a huge amount of computation on like giant linear algebra express models. It's got a pretty diverse package ecosystem for people who need things like HDF5, which is a binary I/O format some of you might have used, which also supports things like parallel I/O, fast Fourier transforms, MPI, first-class ODE solving through things like sundials, and lots of other packages that are really useful for people doing either computational science or data analysis. And another way of expressing that it sort of addresses this two-language problem is to say that when I'm writing my simulation, I can write the model the parameter arrays that I want to examine for that model, for instance, like couplings in the energy function that describes the physics. I can write a job submission script that will ask the nodes, please do this work for me. I can write fast performant numerics code to actually simulate the physics. I can analyze the data and plot it all in one language, and actually sometimes even in one script file that isn't 2,000 lines long, which is pretty great. Okay, so for example, part of my research involves something called tensor network methods, where we try and understand physics by examining the couplings between local matrices or higher ranked tensors, and then optimize those tensors to get a good picture of what the ground state or other low energy states might look like. And so one thing that's great about Julia is that you can just write high ranked tensors, like rank 6 objects, and they just work. They're indexed efficiently. It's great. You can multiply them, slice them, do whatever you want with them, which is really useful for us because you don't have to reinvent the wheel of tensor operations every time. Julia also has really great native distributed and shared memory parallelism. So for example, if you were running a computation across 10,000 nodes, each of which has 48 CPUs, you want to be able to spread information among the nodes, which can't naively access each other's memory, and then within a node have the CPUs share the local RAM, which is also easy to do and efficient, both in terms of the actual time performance and how long it takes you to write the code, which is important. Julia also supports, from the get-go, really nice and easy unit testing, logging, and documenting features. And in scientific code, this is a big deal. A lot of scientific code really isn't unit tested at all. It's not very good. There's actually like a very famous situation where there were about 3 or 4 gold standard codes for a method, and people finally said, we should really run these and compare them on like a very simple model. And they did, and none of them gave the same answer. And everyone was like, wait, what? But we've been using these to solve these much more complicated things where we really have no intuition. So which is right, and it was like a 10-year odyssey of finding bugs in this. And having easy unit testing is one way to help people address this problem. Because in many situations, writing unit tests is so painful that people won't do it. They'll agree, I really should be unit testing, but they don't want to because it's a real pain to both write the tests and run them. Julia also has great logging and documentation features, which are, again, very useful for scientific code. Scientists are also not the best at documenting code or at keeping the documentation up to date. So being able to do that right next to the code is really, really useful for us. And then finally, Julia's type system lets us express some of the concepts that are useful for us in a variety of different ways, some of which I will show you in a second. So for example, there's going to be a lot of linear algebra examples in this, so sorry if anybody here really hates linear algebra. If anybody here is like a Galois theory person, I'm sorry. There's going to be like none of that in this. So Julia supports multiple dispatch, which of course to Python people is probably pretty familiar. So here we've got an example where I want to compute an LU factorization for some matrix A. And of course A could be a variety of different matrices. It could be a sparse type. It could be just some sort of regular old matrix, which is expressed this abstract array type. Maybe I want to use pivoting, maybe I don't, which is what a couple of these are giving me the chance to do. The thing I pass to the LU function could already be factorized, in which case I really don't have to do anything. Or it could be a very simple case where the thing I'm passing isn't really a matrix at all, it's just a simple scalar, which is also pretty simple. What Julia will do is it'll fall back to the correct specialized method if for instance, I give it a sparse type, and if not, it'll call the generic method, which might be a little bit slower, but you don't have to keep writing overloaded operators for every single type you've defined. You can just simply fall back to a generic, provided your type has indexing, which again is probably pretty familiar to you, but this sometimes freaks out people who are used to doing linear algebra in like Fortran. And it's actually, for us, a very useful feature because it makes our code a lot easier to read. So since we're talking about linear algebra, what specifically would you need to do if you were doing physics? Generically, you need to do a lot of operations on pretty small objects, and then a couple really costly operations on very big objects. For instance, you might if you're trying to solve a many-body quantum system, need to diagonalize a matrix that's like 2 to the 36 by 2 to the 36, which is pretty big. It's going to be hard for you to do. But then constructing that matrix is going to require you to do lots of small operations on small vectors. So it's very easy to use things like RPAC methods, which are probably familiar to people who are used to doing numerical linear algebra, like eigs and SVDs. But there's also a nice ecosystem of packages that let you do, for instance, subspace iteration or other matrix vector operations in a parallel way that lets you just call something that's been optimized, and it works really well. And sort of continuing on the LU example, Julia has a really nice type annotation system that's going to let us carry around information about the matrix. For instance, as we'll see on this slide, you can inform Julia's type system with what's called a type tag that the matrix is Hermitian, and then you can simply call the eigensolver on it, and it'll fall through to the correct LAPACK method that calls the Hermitian eigensolver. You don't have to remember, is it eigs or eigs-h or h-eigs? Or where is the h in this function name? You can just call eigs. So here's an example. This is actually some code I have used showing how Julia's types work, including with the linear algebra. So we're going to use the linear algebra part of Julia's standard library. We're going to define an abstract type Hamiltonian, which is like a supertype. So the Hamiltonian is this giant linear operator that describes the interactions in the system, and solving it effectively gives you all the information you need to figure out, what phase is the system in, what's its response to perturbations if I smack it or heat it up. So if you've solved the Hamiltonian, you've solved everything. Basically, many-body quantum physics is a long career in diagonalizing giant matrices. So you got to be able to do this efficiently. So we create a supertype or abstract type Hamiltonian, which has no members. And then we'll form subtypes of it, or child types, which do have various attributes, but they'll all be able to use features that the type system is aware of their super abstract type Hamiltonian. So for instance, Hamiltonians are always Hermitian because the eigenvalues of the Hamiltonian are the energies of the various quantum states, and energies better be real numbers. And the eigenvalues of a Hermitian matrix are always real. So we can automatically say that anything that has a Hamiltonian type or a subtype is Hermitian. We can tell the linear algebra system how to compute the eigenvalues of a Hamiltonian. And then we can construct a subtype. So here we've got a struct Ising, which is a subtype of the Hamiltonian. So the Ising model is a very famous and somewhat simple model for quantum spin systems. It has various phases that represent either a ferromagnet or a paramagnet, depending on the specific parameters that you have. It's also actually pretty related to Conway's Game of Life, if anybody's familiar with that. If you look it up, you'll see that the two of them are pretty similar, but it's basically the simplest quantum model we can write down. And so we say that this thing is a subtype of Hamiltonian. It's got some members, H, the actual matrix, which is Hermitian. So when we feed that into the eigensolver, it's going to correctly do the right thing, deal with LAPACK for us. We don't have to worry. Some parameters, J and little h, which control the couplings in the system and the system size. And then by extending methods in Julia's base and standard library, we can easily feed through our custom type into all of the pre-built linear algebra architecture, which is really nice. So in this toy example, I've constructed an Ising Hamiltonian. I already know what the matrix is and the coupling parameters. I ask, is it Hermitian? Yes, it must be, because Ising is a subtype of Hamiltonian. And I compute the eigenvalues, which are simply fed through to the eigensolver. This is a pretty simple example because the matrix is going to be diagonal, but you could easily imagine writing more complicated constructors where, for instance, you form the matrix object yourself, or you give it an implicit function to compute matrix vector products, whatever. But from the perspective of doing physics, this is really nice because it lets us easily sort of organize our thoughts about the relationships between different models, and also provide guarantees to the eigensolver, like this is Hermitian, or this is, if you wanted like a two-dimensional, three-dimensional model where there's different rules about the size of the Hilbert space, or whether you want to represent things as an explicit matrix or as a matrix vector product, or other similar things. Okay. So I mentioned that Julia has great testing. This is an example where, again, you just use the test module. We're testing some properties about bidiagonal matrices here. And you can organize things into test sets. You can say, like, I want to test everything about making a bidiagonal matrix, which is a matrix where there's the diagonal is filled in, and then either the diagonal right above or right below that is also filled. So there's some basic properties that these things should all obey. Bidiagonal matrices are always square. And if I put a vector on the upper diagonal, the lower one better be empty. And what's nice about this is if one of these tests fails, Julia will say, like, hey, you had a failing test, and it was in the constructor and basic properties section. So you don't have to go and like dig through for line 1054 and just kind of figure out what was in there. You can determine exactly what's going wrong in your code. And you can say, it was actually in the constructor and basic properties for the lower bidiagonal matrix rather than the upper one. I don't know how you did that wrong, but somehow you managed to do it wrong, so fix it. Another thing that's really nice is you can combine this with documentation. If you wanted to document building a bidiagonal matrix, you can actually include an example as a doc test, which when you build the documentation will run. And I believe there are a bunch of Python packages that have this too. I think NumPy does this, where when you build the docs, it'll make sure your example actually works, so you don't have a set of documentation with examples from 5 versions ago, none of which run. Again, also a common problem in scientific computing. And this makes it really easy to both document your code and for other people to figure out how to use it. And it makes it seamless enough that it actually encourages people to write documentation, because it's not that useful, as I'm sure many people here know, to have a documentation system if nobody actually uses it. There's sort of a rubber hits the road factor of like, if you build it, will anybody come? The documentation system is only as good as how much documentation people actually write with it and the quality of that documentation. So Julia's system makes it really, really easy to produce high quality documentation with working examples, which is really a breath of fresh air in a lot of computing code for scientists, especially because you can do this for the numerical code that's often difficult for people to understand, rather than just your analysis code, which was often the situation previously. Okay. So I mentioned also that Julia has great parallelism. There's varying degrees of control you can have. If you just want to call map and just run a bajillion parameter iterations, that's fine. You can totally do that. You can just call a parallel map on some workers. It's great. So here, I've got an example where I construct a matrix, A, which is just some random numbers. I call a parallel map on it. And what's nice about this is the structure of the input matrix will be preserved. For instance, if I pass like a matrix of parameters, it'll come out in the same format it went in. And there's also a bunch of packages that let us control like the cluster. You can just start running a REPL and allocate like 1,000 nodes and start queuing tasks on them. But if you want maybe you're more experienced or you really like doing async for some reason, you can also set up your own parallel constructions using like asyncs and futures and channels if that's sort of more of the paradigm you're coming from. So if you want fine-grained control, you can have it, but you don't need it to get things done, which is pretty great. This is a bit of a shout out to any HDF5 fans here. We use HDF5, which is a binary output format that you can call in parallel pretty often in science. Doing HDF5 IO in C or C++ is maybe not that great, if anybody's used that API. In Python, it's really great. And the Julia API is quite similar to the one in Python. It makes doing high throughput I/O really, really easy. And this is actually a great example of how Julia, I think, has really benefited from the existence of the Python community. Because Python's been around so much longer, we've been really able to benefit from the wisdom of people who've been trying things, seeing how well they work for like 20 years. So we can just sort of hijack their received wisdom about what's the best way to represent this operation, use it, and we can both benefit from improved, for instance, I/O in both languages. Another thing that's really great is we also have sort of Jupyter notebook support. The JU in Jupyter is for Julia, the Pi obviously, and I guess the T is for Python. And there's a lot of really nice plotting and visualization packages. It's not clear that the community is entirely settled on one, which is great. You can pick whichever one you like. So for example, this is a plot made in the LaTeX plotting package, PGF plots. And because, like in Python, Julia codes aren't binaries, they're really easy to port between various systems, like on Windows or on, the Linux cluster to your Mac desktop or whatever. And it's really easy to do interoperability with Python or Fortran or C. There's a great package, pycall.jl, which is looking for contributors if anybody wants to contribute, which allows you to call Python code very easily. So for instance, it's really easy if you just really love matplotlib and you really want to make matplotlib figures from Julia, it's extremely easy to do. So if you are interested in checking out some specific things, there's some research publications that have been made with Julia at this link. If you are interested in various science applications, Celeste.jl was, I think, the largest Julia parallel run ever. It was on this NERSC Copper supercomputer across like 10,000 nodes with some number of CPUs each that does binary star classification. There's a Julia Astro GitHub organization. There are quite a few people working on biological problems in Julia, including the BioJulia org on GitHub. For condensed matter people, if there's anybody else out there, Jutho Hagerman's TensorOperations.jl is great, or there's this quantum optics package. And another thing that you can actually do in Julia, which I think is now also possible in Python as well, is you can write CUDA kernels natively in the language, which are directly compiled by LLVM to PDX, so you don't have to go through some sort of weird C middle layer. You can just directly write GPU code. And finally, there are quite a few nice packages out there for visualizing things or making nice plots. So some short takeaways are that if you want to write very fast code that's readable, Julia is definitely something to consider. The community is really great. It's full of smart people who are very kind, always interested in learning different things. Our package ecosystem is growing and getting better all the time. There are actually quite a few packages for doing, for instance, like UI building or web applications. We also have a Swift wrapper if anybody wants to do Swift. And now that Julia 1.0 is out, you can expect a lot more stability in the language for building packages off of or for working on base itself. And whether somebody is a beginning programmer or experienced or knows a lot about Julia or nothing, we would be super excited to have you. And my pulsing heart. So thanks, everybody. Thanks for your time. And if you have any questions, feel free to ask. I'm probably going to be at the unconference at various points. Whether your question is about Julia or about some condensed matter thing, either is fine. And I'm also doing the panel about first-time open source contributing later today. So thanks for your attention. Oh, question? This one?
Thanks for the great talk. Now I know a lot more about what Julia can do. Can you tell me a few things that Julia can't do that you'd like it to be able to do, particularly when considering like the really large Python data science stack that we have today?
Yeah, so I have to give a caveat first, which is I'm not a data scientist. So that part I may not be able to address as well. One thing I will say that is very frustrating is that although the plotting packages that exist now are like pretty good, there definitely is a lot of room for improvement there. And if anybody watching this is a Julia plots developer, I say that in a loving way. But I think the plotting ecosystem still has a ways to go. This was more of an issue before 1.0 came out, but definitely stability was an issue because things would break every release. And of course, if you're working in a company, that's like not probably acceptable for you. You know, if your boss is like, hey, we need to run this in production for 5 years, and you're saying, okay, cool, but the next release is gonna break everything in 3 months. So that's definitely also not so awesome. I would say from a performance perspective, Julia does have some good performance analysis tools, but definitely the learning curve there is quite steep. So for your average person trying to get started, if their code is slow, it's not necessarily the easiest thing in the world for them to figure out why that is. And Julia people will say, you know, like, oh, well, it's inference, so just fix your types, man. And someone who's starting out will be like, okay, well, that's cool, but I don't know what any of that means. And then they're like, cool, well, just read this 20 pages of documentation, it's fine. But that's not fine, because that person needs to perform a code. From the data science perspective, so we do have our own implementation of data frames and like query and stuff like that, but my sense is that that's not as mature as it could be, and those people are still looking for contributors. Let's see. Trying to think if I can think of anything else that's like a wish list for things to get better, especially for the sprint that's happening this weekend.
How about natural language processing of any sort?
Any NLP, I honestly don't know very much about. I can put you in touch with someone who does that like full time. Sorry.
No, that was a great answer.
Okay.
Also, I'll just add that people coming from the R ecosystem have the same concerns about Python for plotting and data visualization as well. And I know there are core devs of several plotting libraries here as well, so, which are great. I just made eye contact with one of them.
Other questions? Oh. Cool, I ended this like really early.
Yeah. Hello. The incentive structure for people in academics don't really in line with making really good code or documentation or unit testing. How do you get around this to promote creating good code?
Well, this is an opportunity for me to plug my boss and employer, the Flatiron Institute. So this is one of our missions, is to create open source codes, like specifically to create open source codes for people in the sciences to use. We're trying to, because as you said, the incentive structure has traditionally not rewarded people who either develop codes for people to use or improve existing codes, or for instance, even like write a bunch of notebooks for people to learn from. That's not rewarded because it doesn't necessarily result in publications. So part of what Flatiron is trying to do is pay people to do this in a way where they have some job security and they can say, you know, I'm going to devote 5 years to building a better code to achieve this. But in general, you know, obviously, I mean, I like where I work and they're wonderful, but not everybody on Earth is going to be employed there. I think in general, we need to find a way to sort of acknowledge people's contributions in the form of packages. For instance, I think there's now a way to DOI your package, which is great. And then, of course, there's a cultural issue. You have to get people to recognize, you know, I cited this package, and that was a lot of work, so that person deserves some credit, you know, when they're being hired or they're on a tenure committee or something. So some of it is, I think we need to have a way to communicate to people who are not as immersed in the open source ecosystem of like, you know, there's this piece of work that exists that represents some extent of like personal effort and then some form of review in the sense that other people will, you know, use the code and submit issues and stuff, which isn't exactly the same thing as what, you know, journal articles consider peer review, but it is a form of peers who are reviewing your work. And there needs to be a way to give credit to that person, and then there's the separate cultural issue of convincing senior people in the field, people making hiring decisions, you know, this is very valuable work, here are all the knock-on effects of publications that were enabled by it, and convincing those people will be helped if you can cite, you know, the package or whatever. But in terms of like actually arguing human beings into taking open source contributions more seriously, that I'm not so sure how to do, because I'm often not very good at arguing anything at senior people. So maybe somebody with more natural language processing or social psychology expertise should take that. But did that answer your question? Okay.
Thank you. So I noticed that there was reference to type inference, and I was just a little curious about the type system of Julia. Do you find that it can kind of get in your way, like some of the more esoteric functional languages? Is it very unobtrusive? Do you have to specify a lot of types for best performance? What is the situation with the type system in Julia?
This is kind of a complicated question to answer. I would say that personally, I find the type system helpful because I think of it as a way of specifying a series of constraints or promises. Because there's only one level of type hierarchy. So in Julia, you have these abstract supertypes, and then things can be subtypes of them, but only to one degree. So for instance, if I go back to my example, come on, where are you? Oh, here it is. Okay, so in this example, right, we had easing, which is a subtype of Hamiltonian. So I couldn't define something that's then again a subtype of easing. So there's only one level of hierarchy, which prevents you from getting into those C++ like virtual class destructor hell. If anybody also has had that experience in C++. So in the sense that if you use the type system as a series of guarantees or promises that like this will always be Hermitian, this has indexing, or for instance does not have indexing, this is or is not a number, or this is or is not made up only of numbers or only of strings, I don't find the type system particularly obtrusive, and it's also like helpful for me reasoning to say, you know, like these are the rules about what this kind of object can do, or what things I'm allowed to do to it. In terms of performance, probably one of the biggest performance gotchas in Julia is so the cloudy, sort of foggy phrase type issues. Whenever the type system has to figure out or has to perform inference to figure out, for instance, like if I'm adding an object that's an integer and an object that's a 32-bit float, what's the correct type for the result to be? That's something that the type system has to do. And you can provide hints to it to say, like, it should always be this type, like this larger type. But if you don't provide the hint, then you'll often have serious performance problems, especially if you're in an inner loop, because over and over again, the type system has to determine, oh, this should be like a much bigger float or something like that. So there are ways to figure out where this system is spending a lot of time, particularly if it's a sort of type inference issue, to say like, okay, what should the resulting type of this operation be? But like I mentioned earlier, it can be annoying for people who are new to figure out how to determine, I have a type problem, where is it happening, why is it happening, how do I fix it? So this is definitely, I think, an area where we could improve. If you've been using Julia for a while, it's not really a problem because you've had to do it a bunch of times, but definitely the first couple instances where you have to figure out, why is my loop so slow? Oh my gosh. And then you realize it's a type inference issue. I've definitely seen a lot of people who are newer to the language sort of sit there looking at it and be like, I don't know what to do now. Can you help me? Which we're happy to do, but it would be great if they could instead say, okay, here's the documentation. It's really easy for me to figure out how to identify this and how to fix it. So hopefully that will be coming more with 1.0. If anybody from Julia Computing is watching this, please. Did that answer your question? Cool. Anybody from that side of the room?
I have a question.
Oh, okay, cool.
So as an undergraduate, I spent a few months involved in high energy physics research, and there was always this ongoing debate between C or C++ and Python. Things like real programmers write C, and, you know. My question is, how widely used is Julia within the physics community, and are there specific subfields within physics for which it's better suited?
This is kind of hard to answer because first, I don't know every physicist on Earth, and I know you weren't expecting me to be like, all right, I called everybody, 15,000 people answered, but I would say it's very variable by field. So for instance, one of the areas I do research in, tensor networks, which is actually an area with some crossover between high energy physics, which for people who don't know, high energy is like what you think of when you think of particle physics or stuff that happens at the LHC. There's connections to cosmology. There's actually a lot of connections between that and condensed matter physics, and one of the ways that's expressed is with tensor networks. So a lot of people in the tensor network community are like really into Julia. We're actually planning to port one of the main libraries we use from C++ to Julia, or at least write a wrapper, which is really exciting. But the tensor network community isn't huge, and there's lots of other areas of condensed matter physics where people do numerics that I like basically don't ever talk to. So one problem I think in the academic physics community is that there's definitely not enough sort of crosstalk or between different areas of physics, which is something that we should work and improve on. So it's kind of hard to answer how much are people using Julia. I do think, though, that it's pretty well suited to like a variety of different problems. Like, obviously, I use it for research, so I think it's great for condensed matter. I know there are quite a few astronomers using it. By subfield of astronomy, I don't know if the solar system people have like different opinions than the stellar structure people. I think they have different needs. And I think there are also like some people in the lattice gauge theory community, which is a kind of Monte Carlo for anybody who hasn't heard this other annoying piece of jargon. There's a lot of jargon in this field. But I think, the different subfields of physics are actually like in some ways very siloed, so it's hard to answer. But I do think if you need linear algebra or parallelism or good ODE support, it's a good option. And then I guess the other thing is just to address maybe something that was implicit at the start of your question, one thing I do like a lot about the Julia community, and I think many parts of the Python community too, is people are trying to get away from this like real programmers do X sort of thinking, where like really I think a good attitude that a lot of people have is real programmers write programs that work and are maintainable, which is, it sounds like a tautology, but I think it's a bit like saying like real writers actually sit down and write. Like it's very easy to sit around like arguing about like, oh, do real programmers do this or that? But at the end of the day, the real judgment is, do you have working code that other people can use and maintain that produces decent results? Okay, then I don't have to like try and fight you about like, well, you wrote it this way or this other way or in this language or that language. And definitely a good experience I've had talking to especially people in the Python community who are scientists, is that they're like, oh, you like this? Well, that's great. What do you like about it? And then we have a conversation, and they say, well, I'm going to stick with Python because it's working for me. And the Julia people are like, yeah, that's cool, awesome. If you ever want to talk about Julia, come see me. But otherwise, like, good luck with your paper. And it's just it's a good atmosphere, like people supporting each other and trading ideas. So I hope there will be more of that in the future. So. Yeah, sorry, that was a very long answer. I hope it answered your question. Oh.
All right, let's give you like 2 seconds to see if there's any last questions, but if not. All right, well, cool. Thank you.